This episode is brought to you by Cisco Educational Premium.
The atom is the basic building block of matter around us. Your body, your clothing, your chair, your bed, even the device you're watching this video on is made of atoms. The idea of the atom is basically the reason why chemistry exists. The periodic table of elements is basically built on atoms. Ever since the idea of the existence of atoms was put forward by the philosopher Democritus, who said that the universe is made of atoms and the void in which they exist. This idea was since given a solid grounding by scientists, particularly chemists and physicists, proving its existence by scientific method. Today, there is solid evidence that atoms exist. And when we say that atoms exist, we really do know what we are talking about. An atom is most efficient as a dense and compact nucleus encircled by rapidly moving orbiting electrons. This concept naturally raises the question, how do electrons sustain their motion around the nucleus without slowing down? This question became a major concern in the early 20th century and led to the development of quantum mechanics itself. During this time, physicists were making strides in understanding atoms and recognized that each atom contained a positively charged nucleus with a considerable mass surrounded by tiny negatively charged electrons. Armed with this general understanding, they sought to construct a more detailed model. Initially, scientists drew inspiration from the solar system with a dense nucleus, the sun orbited by smaller particles, the planets. However, this model posed two significant issues. First, charged particles that accelerate must emit electromagnetic radiation by observations and at least by Maxwell's equations. Since electrons are charged and accelerate during their orbits, they should emit radiation which will cause them to lose energy and quickly spiral inward into the nucleus. However, atoms are known to exist far much longer than a picosecond, making this model incorrect. Secondly, atoms were observed to emit radiation at specific frequency, unlike the continuous emission expected from an electron following the solar system model. Niels Bohr, a renowned Danish physicist, was the first to propose a solution to these problems. In 1913, he suggested that electrons in an atom do not just occupy just any orbit but confined to specific distances from the nucleus. He also proposed that there was a minimum distance an electron could reach beyond which it could not move any closer to the nucleus. Bohr's ideas were not just mere speculations. They were built on the work of German physicist Max Planck, who had proposed the quantization of radiation emission a little over a decade. According to Planck, objects could only absorb or emit radiation in discrete chunks, not in any arbitrary value. These discrete chunks were characterized by constant value known as Planck's constant, which had units akin to angular momentum. Bohr adopted this concept and applied it to electrons orbiting a nucleus. He asserted that the smallest possible orbit of an electron will have an angular momentum equivalent to 1 Planck constant. High orbits would have integer multiples of the Planck's constant, such as twice or 3 times its value, but never fractions like half or 2 and 3. The full comprehension of why electrons possessed specific orbits and well-defined energy levels required the more complete development of quantum mechanics. Electrons, like other matter particles, exhibit both particle and wave behavior. While we might envision an electron as a tiny planet orbiting the nucleus, we can usually visualize it as a wave enveloping a nucleus. Waves confined within a limited space must adhere to specific rules. They cannot have arbitrary wavelengths. Instead, they must consist of standing waves that fit precisely within the space. This analogs to playing a musical instrument. When you fix the ends of a guitar string, only specific wavelengths produce distinct notes. Similarly, the electron wave cycling a nucleus must fit the available space, and the nearest orbit is determined by fast standing wave of that electron. Future advances in quantum mechanics would continue refining this model, but the fundamental point remains unchanged. An electron cannot approach the nucleus any closer due to its inherent quantum mechanical constraints, which prevent it from occupying smaller space. However, an entirely different approach to understand this situation do not rely on quantum mechanics at all. Instead, it considers the various energies involved. An electron in orbit around the nucleus experiences electrical attraction towards the nucleus, constantly being pulled closer. At the same time, it possesses kinetic energy trying to propel it away from the nucleus. For a stable atom, these two forces are in equilibrium. In fact, the total energy of an electron in orbit, which combines its potential and kinetic energies, is negative. Consequently, adding energy to the atom is necessary to remove an electron. This concept parallels the behavior of planets orbiting the Sun. To remove the planet from the solar system, energy must be added to the system. One way to envision this scenario is to picture an electron falling inwards towards the nucleus due to the attractive electric charge. However, because of the principle of quantum mechanics, the electron can never reach the nucleus, becoming perpetually in a stable orbit. Nevertheless, this situation is permissible according to physics because the total energy of the system is negative, signifying its stability and binding components together to form a long-lasting atom. Everything around us is composed of atoms. All the matter in the observable universe is estimated to be more than 10 quadrillion quintillion. This number is 1 followed by 78 zeros. Atoms are tiny particles consisting of electrons, protons and neutrons, which are in turn made up of quarks. The origin of these particles that make up atoms can be traced to the Big Bang. The Big Bang theory explains the beginning of the universe, where an immense amount of energy condensed, leading to the formation of atoms. There are more technical details than this, which we are going to look at them. To understand the scientific perspective of the Big Bang, we need to examine the events of the early universe. Unfortunately, we do not have a definitive understanding of precisely when the universe started, or if it indeed started at all. Our base model, the standard model of cosmology, allows us to trace back time close to the beginning, but we encounter a barrier at t is equal to 1. This theory predicts a singularity, a moment of infinite density where all matter and energy were compressed into an infinitely small point. Most physicists predict that this prediction may not be entirely accurate. We can only go back to one Planck time, which is about 10 raised to negative 43 seconds. Before this, we have no knowledge of what occurred both by observation and mathematics. So while we get very close to the beginning, it is not precisely at t is equal to 1. Understanding the events of this incredibly small time scale requires a quantum theory of gravity, where gravity, which explains the behavior of large objects, meets quantum mechanics, which governs the behavior of particles at tiny scales. The epoch of the universe, known as the Planck epoch, occurred at 10 raised to negative 43 seconds. During this time, it is believed that all the fundamental forces, including electromagnetism, the weak force, the strong force, were unified as one grand unified force at this point. However, it is important to note that this isn't exactly t is equal to 1, as we want to avoid the singularity. The state of the universe at this epoch and what happened before it remain unknown. The earliest time we can theorize about is the period of inflation, which occurred from about 10 raised to negative 36 seconds to about 10 raised to negative 33 seconds after the Big Bang. During this time, whatever existed prior to inflation experienced rapid exponential expansion, faster than the speed of light. This is allowed because there is no theoretical restriction on the speed at which space itself can expand. It expanded from a point to a point about the size of a baseball. You might wonder how this is even possible, since we know that nothing can travel faster than the speed of light. While this is true for information transfer, cosmic inflation involves the expansion of space itself, allowing distant points to move away from each other faster than light can travel between them. Most of our current understanding comes from the period after inflation. So the accurate way to view the Big Bang is not as a single point of origin, but as a period when the early universe was extremely hot, dense, and rapidly expanding. Thus, the Big Bang is a description of everything that occurred after t is equal to 1. Inflation is believed to have occurred from 10 raised to negative 36 to 10 raised to negative 3 seconds. The energy source behind this rapid expansion and cosmic inflation erased any information about what existed before it. The theory of the standard model of cosmology is well understood, starting at about 10 raised to negative 12 seconds, as the universe's energy levels can be reproduced in current particle accelerators. Before this time, we can only speculate about the events. From about 10 raised to negative 3 seconds to 10 raised to 12 seconds, strong force and electromagnetic and weak forces, collectively known as electroweak force, was still unified. The origin of the initial massless fundamental particles is uncertain. They might have condensed from the energies present during the Big Bang, or an inflation field containing inflations could have decayed into the fundamental particles we observe today. Around 10 raised to negative 11 seconds, the temperature drops further to 10 raised to 15 Kelvin, marking the beginning of the quark epoch. The electromagnetic and weak forces begin to separate, leading to electroweak symmetry breaking. The X fields gains a non-zero potential, imparting mass to the fundamental particles of the standard model. At this point, the essential components of atoms are in place, and the universe temperature is around 1 quadrillion Kelvin. As the universe continues to expand and cool, the extremely high temperatures present prevent quarks from combining into hadrons like protons and neutrons. However, as temperature drops to about 1 trillion Kelvin at 10 raised to negative 5 seconds, the quark plasma transitions into a hadron gas consisting of protons neutrons, and certain mesons, which eventually decay into photons and electrons. As the temperature further decreases, particles and antiparticles begin to annihilate, resulting in lighter particle-antiparticle pairs, such as neutrinos and photons. Interestingly, there is a slight asymmetry in this process, which with more particles being generated than antiparticles, leading to the survival of certain quarks and electrons. This enables the formation of protons, neutrons, and electrons, which are essential for creating the initial atoms. The annihilation process culminates with the Lipton epoch, which occurs around 1 second mark when the temperature subsides to about 5 billion Kelvin. During this epoch, leptons conclude the annihilation process. Following this remarkable display, the majority of the matter particles transforms into photons and neutrinos. However, due to the matter-antimatter asymmetry, a small quantity of protons, neutrons, and electrons remain surviving as the fundamental building blocks for atoms. At around a few minutes after the universe's inception, the epoch of the Big Bang nucleosynthesis (BBN) begins with protons and neutrons produced in equal numbers. Free neutrons are inherently unstable and undergo beta decay, transforming into protons over approximately 10 raised to 50 minutes. As the temperature remains high, proton-neutron conversion is balanced by neutron-proton conversion. But as the universe cools further, neutron decay becomes more prevalent. Free neutrons strive to join other hadrons and form more extensive nuclei before decay, leading to the universe consisting of about 75% hydrogen nuclei and 25% helium-4 nuclei, along with small amounts of deuterium, helium-3, and trace quantities of lithium-9 nuclei. During this period, the environment predominantly consisting of ionized nuclei without bound electrons. The formation of neutral atoms requires electrons to attach to positively charged nucleons to achieve charge balance. However, the universe is still scorching and electrons can only briefly adhere to nucleons before being forcibly separated due to their immense energy. As a result, the universe remains opaque and photons carrying light continuously interact with nucleons and electrons, hindering their free propagation through space. This photon epoch lasts for about 380,000 years until the universe cools down to 3000 Kelvin. At this point, electrons possess significantly reduced energy, allowing the electromagnetic force to permanently bind them to nucleons, leading to the formation of stable neutral atoms in a process called recombination. As a consequence, photons are no longer confined amidst the chaos of positive nucleons and negative electrons. They are now free to traverse the universe. If an observer was present in space, he or she would be able to observe this light. Today, the first light of the universe, known as the cosmic microwave background (CMB), can be perceived in all directions. This light was emitted during the formation of fast stable neutral atoms, providing us with valuable insights into the early universe and the origin of atoms. Atoms constantly interact. However, to comprehend this, we must first determine the definition of interact. Our typical understanding of interaction is based on the macroscopic world. I place my palm on the chair. My palm interacts with the chair. You step on the floor, you interact with the floor, and so forth. In these instances, one solid boundary or surface interact with another solid boundary or surface. Nevertheless, our macroscopic understanding becomes less applicable at a microscopic level, which lead to confusion about interaction. If we could magnify the scale to atomic level, we would witness a chaotic environment. Atoms and molecules are consistently in motion, colliding, twisting, and spinning, resulting in a chaotic scenario. However, one thing becomes evident: atoms lack a definite boundary. They exist a nucleus, a collection of protons and neutrons at the center, surrounded by clouds of probabilities that indicate the potential locations of orbiting electrons. The principles of quantum mechanics allows us to calculate probabilities which extend through the entire universe. Nevertheless, in nearly all observations, electrons remain securely bounded to the nucleus. So unless we are conducting high energy collider experiments, we don't have to worry too much about it. Since atoms lack a firm surface in a way, there's no tangible touch because there is never a direct meeting of the boundaries. However, touch also implies close and influential interaction, and in that sense, atoms are in constant contact. Atoms interact due to the electromagnetic force which arises from the electric charges of the protons and electrons within them. Technically, this force has an infinite range, but it becomes significant only when atoms are significantly close. At times, atoms literally repel each other due to the electromagnetic force between their electrons. In that brief movement, it is challenging to describe their interaction as anything but touching. Even if the interaction is not momentarily, it still qualifies as touching. For instance, when we examine the palm at the chair at the atomic and molecular level, we notice that the electrons at the palm outer edge are repelled by the electrons on the chair's outer edge. Despite the gap within the layers of electrons which typically exist, the atoms are close enough to significantly influence each other. This is evident from the fact that the cup does not fall through the chair, and the electromagnetic forces between the atom counteract the gravity's pull of the cup. At the macroscopic scale, when we say two objects are touching, it reflects the same interaction at the microscopic level. Atoms can also touch through other means. As electromagnetic force is not always repulsive, when atoms get close, the van der Waals force, the manifestation of the electromagnetic force, can lead to bonding between atoms. This process results in the formation of molecules, where the atoms inside them are definitely in contact. Lastly, even nuclei within atoms can touch, although it is extremely difficult due to the strong electromagnetic repulsion between the positively charged protons in each nucleus. Yet quantum mechanics play a role here too. If two atoms are brought close enough and maintained for sufficient time, occasionally and randomly, their nuclei can intermingle. This phenomenon leads to nuclear fusion, where two separate atoms merge into a single larger atom. If the atoms involved are lighter than iron, the fusion process releases energy. It is through this mechanism that all stars, including our sun, generate their power. Two atoms of the same element are typically non-indistinguishable. First, electrons in an atom can occupy a range of possible states. Therefore, two atoms of the same element can be different if their electrons occupy different states. For example, one copper atom with an electron in an excited state and another copper atom with all electrons in the ground state are distinct. The excited copper atom will emit light when the electron returns to the ground state, while the copper atom in the ground state will not. The nature of the chemical bonding experienced by an atom depends on the state of its electrons. So two atoms of the same element can react differently if they are in different states. We chemists are aware of this fact. And to fully describe and predict a reaction, it is necessary to specify excitation states of the electrons in the atoms. Additionally, even when left alone, an atom often does not have an equal number of protons and electrons. However, even if two atoms of the same element have their electrons in the same state, they are still not identical. For example, they could be traveling or rotating at different speeds, which influences their ability to chemically bond. Slow moving atoms, such as those in solid iron, have time to form stable bonds, whereas faster moving atoms, like those in liquid iron, cannot establish such stable bonds. As a result, a slow moving thin atom is different from a rapid moving thin atom. But what if two atoms of the same element both have their electrons in the same state, and the atoms are both traveling and rotating at the same speed? Then are they indistinguishable? No. Although two such atoms are essentially chemically identical, they will chemically react in the same way. They are chemically identical. Beyond the electrons, there is also the nucleus to consider. An atom's nucleus contains tightly bonded neutrons and protons. The same chemical element can have different number of neutrons and still be the same element. These atoms with different number of neutrons are referred to as isotopes. While a particular isotope involved does not impact an atom's chemical reactions, it does determine how an atom behaves in nuclear reactions. Radioactive decay, the most common nuclear reaction on Earth, varies among different isotopes. Some isotopes decay rapidly into other elements and emit radiation, while others do not. For carbon dating, the fact that carbon-12 is not the same as carbon-14 atom is crucial to the dating process. Simply counting the number of carbon atoms in a sample will not provide information about the sample's age. Instead, you have to count the number of different isotopes of carbon. But what if two atoms are of the same element, have electrons in the same state, and traveling and rotating at the same speed, and have the same number of neutrons? Then are they indistinguishable? No, just like electrons, the neutrons and protons in the nucleus can exist in the various excited states. Additionally, the nucleus as a whole can rotate and vibrate at different speeds. And even if all else is identical, two gold atoms can have their nuclei at different excited states and behaves differently in nuclear reactions. In summary, achieving two atoms of the same element to be perfectly identical is exceedingly difficult. In fact, such an accomplishment will be a Nobel Prize worthy. Nevertheless, it is important to note that atoms do not possess individual identities beyond what has been mentioned here. If two carbon atoms are in the exact same molecular, atomic, electronic, and nuclear state, then those two carbon atoms are identical regardless of their origin or past history. Everything has color. Since almost everything have color, atoms as the fundamental building blocks of reality should also have color. Or does it? When you aggregate numerous atoms together, you obtain the screen that you are constantly observing, which indeed has color. So, does it imply that each individual atom has its own color as well? If so, is it the nucleus or electrons that are painted? And if so, what color? The color we perceive are a creation of the human brain. They don't actually exist outside our visual perception. So then, what precisely is color? To understand this, we need to comprehend the nature of light. Light consists of photons, which are particles. However, This behavior is only evident when observed. Otherwise, they tend to act as electromagnetic waves. This phenomenon is known as the wave-particle duality concept. And yes, it is peculiar. These waves possess specific frequencies, and depending on their frequencies, they are classified to 7 primary wavelength sections, ranging from radio waves with wavelengths the size of Earth to gamma rays the size of atoms.
Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.
Yeah.